Have you ever wondered how some materials can be both soft and strong at the same time? Or how engineers design lightweight structures that can survive a strong impact and still return to their original shape? Or imagine this, you fall off a bicycle, your helmet protects you, but after that one crash, it's useless. What if we could create materials that don't just protect us, but also bounce back and can be reused?
Assalamualaikum and hi, my name is Nordini binti Muhammad Nazri, and in this video, I'll be presenting a research article titled Energy Absorption in Lattice-Structured Materials Under Impact Loading, which connects directly to a key topic we have learned in PHY 535, lattice structures, unit cells, and crystal geometry.
So what are lattice-structured materials? These are materials made from repeating 3D geometric shapes, just like how atoms are arranged inside a crystal. The smallest unit that repeats is called a unit cell, and when you connect many unit cells together, you get a lattice.
These lattice structures are not only lightweight and strong, but they also have interesting behaviors under stress, especially when heat or compressed. That's why they are widely used in protective gear, packaging, and aerospace parts. In this study, scientists tested different 3D printed lattice designs made from soft materials to see how well they can absorb impact energy and return to shape after compression. Throughout this video, I will take you through their process, findings, and how this study brings our theory from PHY 535 into the real world. The researchers tested 5 different 3D printed lattice designs, each made from a soft TPU-like resin using SLA printing. To compare their strength and energy absorption, they printed each structure in 3 relative densities, which is 0.2, 0.3, and 0.4. Instead of changing the size of the structure, they adjusted the strut radius, which changes how much material is inside the unit cell.
In figure 3a, we can see that as the strut radius increases, the relative density also increases. This allowed the researchers to control material usage while keeping the overall shape the same. To simulate real impact, the printed samples were tested using a split Hopkinson bar or SHB setup. The striker bar hit the samples at a speed of 15 meters per second, compressing them up to 80%. The impact response was recorded with strain gauges and a high-speed camera at 30,000 frames per second. Each test was repeated 3 times to ensure consistent results. Here are the 5 lattice designs tested in the study. All of them are built using 3x3x3 unit cells, and their shapes are inspired by real crystal structures that we learned in PHY 535. For example, the octet is based on a BCC-like structure, while diamond mimics the carbon atom structure in crystals.
In figure 2, you can see the unit cells of each design. These repeating units form the full lattice, and their internal geometry plays a major role in how the material behaves under impact. This variety of shapes helps researchers study how different geometries affect strength, flexibility, and energy absorption. 2 key parameters in this study were relative density and the Maxwell number.
Relative density, written as ρ, tells us how much material is inside the structure compared to a solid block. The researchers tested all designs at 3 densities, 0.2, 0.3, and 0.4, and controlled it by changing the strut radius, which you can find in table 2. The Maxwell number, labeled M, tells us how the structure behaves when force is applied. If M equals 0, it means the structure is stretch dominated like the octet. But if M is less than 0, it's bending dominated, which means it absorbs energy by folding or flexing, like diamond, BFCC, Tran-octa, and Rom-octa.
In table 1, we can also see the number of struts and nodes for each unit cell. which helps explain how the structure handles load. More nodes can mean more complexity in force distribution. Let's now look at how the impact tests were conducted. The researchers used a modified version of the split Hopkinson pressure bar, or SHBP, which is shown here in figure 5.
In the experiment, a metal striker bar was launched at a speed of 15 meters per second toward the sample, which was placed between two bars. This impact generated stress waves that traveled through the sample. The setup included strain gauges to measure how the stress moves through the sample and a high-speed camera capturing the deformation at 30,000 frames per second.
Each sample was compressed by up to 80%, and the test was repeated 3 times for each of the 5 lattice designs across all 3 density levels. This allowed the researchers to collect accurate data about energy absorption and reversibility strain behavior during impact. As you can see in figure 5, this setup allows us to measure what happens when a sudden force is applied, helping us understand which lattice structures perform best. Now, let's take a look at how the lattice structures behave when hit with high-speed impact. The samples were compressed by up to 80%, which is quite extreme. But the key question was, can these materials bounce back to their original shape after being squashed that much? The researchers used a high-speed camera running at 30,000 frames per second to capture the full deformation process in real time. Let's look at some of the results.
In figure 6, you can see the octet structure made from ABS-like material before, during, and after the impact. Figure 7 shows the same octet structure but made from TPU-like material, which is softer and more elastic. And in figure 8, we see the diamond structure, also made from TPU.
As you can see in the images, even after being heavily compressed, the TPU lattices were able to recover almost fully to their original shape. This proves that these materials can be reused after impact, unlike typical foams or plastics that break or stay deformed. The experiment shows that geometry and soft materials will get reversible protection, which is exactly what we want in reusable safety gear or packaging. Let's now look at how much energy each lattice structure absorbed during the impact test. This is one of the most important results of the study.
In figure 12a, we can see the total absorbed energy for each lattice type across the 3 density levels. And in figure 12b, we see the specific energy absorption, which tells us how efficient the material is, basically how much energy it absorbs per unit of its mass. The results are clear. Tran-octal and Rom-octal absorb the most energy overall, especially at higher densities. The diamond lattice consistently showed the lowest energy absorption, making it the least effective for this application. We also see a pattern. As density increases, the total energy absorption goes up, which makes sense because there's more material to absorb the force. But interestingly, the SEA is highest at the lowest density, 0.2, meaning these structures are most efficient when they are light.
This is important in real-world design. If you want lightweight protective gear, like in aerospace or wearable equipment, you want materials that give you high performance with low weight. Tran-octal and Rom-octal are clearly the best options for that. So in short, the shape of the lattice matters more than the material itself. Choosing the right geometry can greatly improve how much energy a material can absorb during a crash. Aside from just measuring energy and deformation, the researchers also analyzed the frequency of the shock waves that pass through each lattice during impact. They did this during a method called fast Fourier transform, or FFT, which takes a time signal like the force of the impact and converts it into a frequency spectrum. This helps us understand what kinds of vibrations are being transmitted or absorbed by the structure.
In figure 11, we can see the frequency spectra for each of the 5 lattice types at a density of 0.3. Each curve shows how much energy is present at each frequency. The main finding here is that the lattice structures act like low-pass filters. That means they allow low-frequency waves to pass through but block high-frequency vibrations. Why does that matter? Because high-frequency vibrations are often linked to noise, resonance, and even damage in sensitive systems. By filtering them out, these lattices could be very useful in applications like vibration dampers, noise insulation, and shock-absorbing materials for electronics or vehicles.
So this result shows that the benefit of lattice structures isn't just in absorbing force. They can also help control how vibrations spread, making them even more valuable for protective and mechanical systems. Besides physical testing, the researchers also use computer simulations to study how lattices behave during impact. This method is called finite element analysis or FEA, and it was done using the software Abacus. FEA allows us to model a complex structure, apply forces to it, and observe how it behaves, even in ways we can't directly see in experiments.
Let's look at figure 13, which shows the finite element mesh used for the simulation. You can see the octet structure broken into many small elements. These elements are used to calculate how the material deforms under stress. In figure 14, we see snapshots from the simulation as the striker impacts the structure. It shows how the compression spreads through the unit cells and how the structure reacts to the sudden force. Then, in figure 15, we get a stress distribution map. The red zones show high stress, mostly around the nodes and joints of the lattice. These are the areas most affected during impact.
The simulation results match well with the experimental data, confirming the accuracy of the physical test and helping to visualize internal stresses that are hard to measure directly. However, the authors mentioned that these simulations are very computationally expensive, meaning they require a lot of time and processing power, especially for dynamic problems like this. So, while FEA is a powerful tool, it's best used alongside physical testing for full understanding. To conclude this presentation, let's look at what we have learned from this research. First, the geometry of a lattice has a huge impact on how well it absorbs energy. Even though all the samples were made from the same material and printed the same way, their performance was very different just because of the shape of the unit cell.
Among all 5 designs, Tran-Octa and Rom-Octa stood out as the most effective. They were able to absorb the most energy and still bounce back to their original shape, even after being compressed up to 80%. That makes them reusable, a big improvement over current one-time use materials like foams. The use of soft 3D printed materials combined with smart design shows how we can create sustainable, lightweight, and high-performing materials for impact protection.
Finally, this research is a perfect example of how the theories we learn in PHY 535, like lattice structures, bases, and unit cells, are applied in real-world engineering and material science. These concepts are not just academic, they are essential for creating the next generation of protective and structural materials. And that's all from me. Thank you for watching my presentation.